So let's look at the graph of y equals x squared. And I want to talk about a thing called end behavior. The graph of y equals x squared, we know is the famous old parabola. Now, over here, as x gets big, a way of saying x gets big is to write x arrow infinity. And I ask, what happens to y? Well, it looks like that as x gets big, the y-coordinate gets big. That is, if we go out here on the x-axis, the y-coordinates are getting bigger and bigger and bigger. And so I would say, as x gets big, y gets big. On the left side, as x goes to negative infinity, that is, x is going back this way, points here, it looks like the y-coordinates again are getting big, and so we would say y goes to infinity, or you can write plus infinity. Now that's called end behavior. So the end behavior for x squared, on the left and the right, the graph heads towards positive infinity. Let's look at the graph of x cubed. Just happen to know what the graph of x cubed looks like, but if I didn't, I could do it on my calculator. I could plot some points. Now this one, as x goes to infinity, y goes to, oh, look at there, it's just like x squared. As x goes to infinity, y goes to infinity, and as x goes to negative infinity, y goes to, in this case, negative infinity. I wonder why that happens. Well, if you just think about it, if you take a negative x that's big and cube it, you get something that's really big negative, right? So that's what produces that behavior back there. Well, I think that would be true of x to any odd power, yes, because if you take a negative number that's big negative, and raise it to an odd power, you're going to get something that's really big negative. So I think x to the 5th, x to the 7th, x to the 9th, x to any odd power is going to have on the left side this kind of end behavior, and on the right side that kind of end behavior. Now, if you have an even exponent, when you put a negative x into that even, you get a positive, so the evens, as x goes to negative infinity, are going to go to positive infinity. That's a nice thing to observe. In fact, that's a very nice thing to observe. Let's go to the calculator here and do a little exploration. Get that stuff out of there. I want to put in here x to the 3rd, x upper 3rd. There actually is a cube in there. Let's see, I think it's in math. And let me go looking for it a little. Let's see, math. Yeah, there it is. So I could have done, well, let me do that. Could have done x, then gone to math, and pushed to number 3. That would put a cube up there. That only took one more button push than to use the caret here, but I guess the reason that I tend to rely on that caret is that the hard part of doing what I just did is remembering where it was. I just happened to remember that was in math. I'm going to put some other stuff. Plus 2x squared minus 5x plus 4. So the Texas Instruments was nice here. They put that x squared button there because, you know, I mean, you use a square a lot. So you want to have to not go to a screen to find that. I wonder what the end behavior of this graph is going to be. Let me think. End behavior is an investigation for a big X or a big negative X. Now, if X is a big number, what is the most significant part of this function? I would think that it's the x cubed, right? I mean, if you think about 1,000 cubed is much more significant than 1,000 squared, yeah? So that's what we call the dominant term, is the x to the biggest power right there. So I believe that the end behavior of this function is going to be very similar to the end behavior of just x cubed, because for big or big negative values of x, that first term there, the dominant term, is going to be the important thing. So I believe on the right, this graph is going to head towards infinity, and on the left, the graph is going to head towards negative infinity. Let me push that graph button and find out. Now let's see, I think zoom number 6 is what I want, and it'll go ahead and graph. So we did get some other stuff wiggling around here, but it does look like on the left we're going to negative infinity, on the right we're going to positive infinity. Now you might say, wait a minute, how do we know? How do we know that we just didn't chop it off and maybe over here it's going to come back down again? Well, again, the way we know that is we thought it out, yeah? So there again we did a combination of brains and buttons. Now let's try x to the fourth. X to the fourth. And I'll put some other stuff in there. I just randomly put some stuff in there. X squared minus 5. I believe this is going to behave very much like x to the fourth. That is, on the left and the right, I think we're going to head towards positive infinity. Let's see. Well, that seems to have come true there too. So the point of all this is it's the dominant term that's most significant.